perfect timing at 4 o'clock. It's time for Jessica's third and last talk on knots and infinite volume hyperbolic three manifolds. Take it away, Jessica.
All right, thanks. So this is the last talk of what has been a really nice conference. So traditionally when we are in person, the final speaker sometimes takes a moment to thank the organizers. And even though we're not in person, I think it's appropriate. If you can all find your applause buttons, we should really thank the organizers for putting together what has been a really great conference that's quite different from these other conferences so far. So thanks very much to all of the organizers. Thank you. All right, so today my talk is on knots and infinite volume hyperbolic three manifolds. It's going to be a little less on the knots today, more on the infinite volume hyperbolic three manifolds. Again, I've got 3 talks planned of different lengths. Actually, let me set a timer to make sure that I'm going about the right speed. Part 1, I want to give a guided tour of infinite volume hyperbolic three manifolds. So a couple of days ago, someone mentioned they're interested in what are some major results in the field since the 2000s. And there are 3 big major theorems I want to talk about today. It's kind of this introduction. Part 2, I want to talk about how do you know from the topology that you get something that's hyperbolic? And then part 3, these tools make life really easy, I think, or a lot easier. So we can apply finite volume results to infinite volume. And I'm going to talk about a recent result of mine with Dave Futer and Saul Schleimer in that talk. Okay, so here we go. Let's start with our guided tour. I'm stating a few things on my slides that are not mathematically rigorous, and I'll try and flag those in blue. The first statement is infinite volume hyperbolic three manifolds are hard, whatever that means. Well, here's what I mean by that. I think that they're more difficult than the finite volume ones for several reasons. Number one, you have no rigidity. So in a finite volume hyperbolic case, if you have a hyperbolic structure, it is unique. So there's only one. Once you've found it, you have it, and you can't do anything to it. But infinite volume, there are uncountably many hyperbolic structures. And number 2, there are multiple topologies on the space of hyperbolic structures that are typically used to explore things. And I'm not really going to talk very much about the different topologies, but an issue with reading the literature is sometimes something is proved in one topology where you actually need a different topology and you don't realize it until you try and use the result and it's wrong. So that's something important to keep in mind. Number 3, once you have these topological spaces or these topologies on spaces of hyperbolic structures, you start looking, you can go out to the boundary of the space of hyperbolic structures, and the boundaries, things get weird. And in fact, some of this boundary behavior is what has been driving the field for about 60 years, what's going on as you are approaching the boundary of these spaces. And then finally, again, it's sometimes hard to read the literature, especially from the classical stuff, the early stuff in the 1960s, because they thought they were doing complex analysis. They didn't realize they were doing three manifold geometry. So, all right, so let me start off just with a quick introduction again. So a hyperbolic three manifold, we've been talking about these for 3 days. But just once more, if you have a hyperbolic three manifold, then its universal cover is hyperbolic three space, which I'll draw again as the upper half space model. So we have C cross R plus, and we've got a metric that makes our geodesics be vertical planes and hemispheres like so. We have a boundary at infinity, which is the Riemann sphere. And the group of covering transformations, this deck transformation group, is going to be a discrete subgroup of the group of isometries. We're sticking with orientation preserving, so this is going to be PSL2C. And these elements in PSL2C, they act on the boundary by just standard Mobius transformation. So you may recall that there are 3 types of elements in PSL2C. So there are elliptic ones. Elliptic ones fix an axis pointwise. So they'll rotate along, right? So if we have a line, they'll just rotate along that axis. That's elliptic. These are not going to occur in the hyperbolic three manifolds because they give singularities. So we're going to rule those out. But the next two do occur. The parabolic ones, they fix a point at infinity. And they translate along that. So for example, they'll fix, they're given by translation along a horosphere. Okay, so I just drew over here in the picture, this is a horosphere. So it's of the form t is equal to some constant. And a parabolic would be something that will take a point on the horosphere and just translates it. So z goes to z plus a, for example. So something in the form 0, 1, b 1 would be parabolic. Okay, and then finally, everything else is loxodromic, and these translate along an axis. And when you quotient out by a loxodromic element, you'll get a closed geodesic in your manifold corresponding to the axis of that. But the parabolic guys, these appear when you have a cusp. So either when you have when we looked at them in terms of the knot complements, then they give you, their quotient gives you, say, a torus out at infinity or on a horosphere, or you can also get an annulus from them. All right, so jumping from geometry back to, not back to topology. First, we're going to do some examples. So I think it's going to be important to do some running examples all the way along. And I have a couple different manifolds that show different properties that are happening when you have an infinite volume hyperbolic structure. The first one is when you have a surface cross an interval. So S is going to be an orientable surface, and it's going to have negative Euler characteristic. Then we'll look at the hyperbolic structures that are on this. Some features is that these manifolds have incompressible boundary. So what that means is there's no disk embedded in the surface cross I whose boundary lives on the boundary of M, except the boundary parallel ones, right? So except trivial. And surface cross I, these are the types of manifolds that will appear in virtual knot theory. So virtual knots live in a surface cross I, somewhere in the middle on a projective surface. The other type of manifold I want to look at that's infinite volume is what I've called here a 1-2 compression body, and you can generalize this, but we'll stick with this somewhat simple case. And it's obtained by taking a thickened torus, so a T2 cross I, and then taking the union of that with a 1 handle. So this is the thickened torus in my picture. And then we attach to that a 1 handle. And as opposed to the surface cross interval, this does have compressible boundary. Here's a disk on inside the 3 manifold that's a non-trivial curve in the boundary. So that's the boundary of the disk is non-trivial. We'll also often call that a meridian, is a compressing disk. And this type of manifold appears in Heegard splittings of certain knot complements. So for example, 2 bridge knots. More generally, any tunnel number 1 knot has a Heegard splitting with this in its decomposition. And again, you can generalize that. So I'm going to show you some hyperbolic structures on these. I think some of the first pictures that have come out around this area were for the surface cross an interval. And this is a picture that is in a bulletin article of Thurston from the early 1980s. It's not a very exciting picture. It'll get more exciting in a minute, I promise. How do you put a hyperbolic structure on a surface cross an interval? Well, if you just look at the surface, because it has Euler characteristic less than 0, it's going to have a 2-dimensional hyperbolic structure. If you look at the Poincare disk model, for example, then a way of drawing a 2-dimensional hyperbolic structure is to take say for a genus 2 surface, you take an octagon. Is that an octagon? I didn't count. Anyway, you take your octagon with all of the angles, it's a regular one with angles 35 degrees, and then this is going to give you a hyperbolic structure on this 2-dimensional surface. And then you take this 2-dimensional surface and you just take your copy of hyperbolic 2 space and you embed it as a totally geodesic hemisphere inside your hyperbolic 3 space, like so. Okay, and so this picture over here is just showing you what's happening at the boundary at infinity. So you get this straight circle. Okay, So that's one way of getting a hyperbolic structure on this, on the interior, I should say, of the surface across the interval. But you can deform that a little bit. So if instead of taking a perfectly straight geodesic surface, well, once you have this group, maybe let me go back to the last slide. Here we're going to get, this is going to be a quotient H3 mod gamma, where gamma, after conjugation, you can really think of it as a subgroup of two-dimensional isometry. So those live in PSL2R. But if you deform this just slightly, so now you are in not PSL2R, but you bump these by epsilon, say in the complex plane, then you start getting pictures that look like this. So these are quasi-Fuchsian. So your boundary is no longer a perfectly straight circle. The boundary here, this is known as the limit set. And it's not perfectly straight, but it starts to deform a little bit, or a little bit more, or a little bit more. And you can see that as you deform it more and more and more, you end up with these fractal curves. So you get these quasi-Fuchsian fractals. Okay, so something very cool is happening in the limit. And I think some of these pictures are motivation for studying the geometry in the limit and for putting topologies on these spaces of structures. What does it mean to deform it slightly in terms of the topology of the space of structures, and what happens as you approach infinity? You're getting these really cool, really complicated shapes. Where do they go if you push them? Okay, second hyperbolic structure. This is on this compression body. So the first thing to observe is that this has a really straightforward fundamental group. It's just the free product of Z with a Z cross Z. So this corresponds to the T2 cross I bit. And then this comes from the one handle. And so when you're looking at the quotient, if we want to write this as the quotient of H3 by a group of deck transformations, you really just need your three elements of PSL2C that are going to be generators that give you this Z cross Z subgroup. So the first two should be parabolic. And I've picked two parabolic ones fixing the same point at infinity. And then the last one should be loxodromic. And what these do is the parabolic ones, they're going to fix this blue plane about infinity. And if you ensure that A and B are linearly independent in the complex plane, then they'll cut out a torus. And then this one over here, this is going to glue the unit disk to a disk with center C and radius 1. And so topologically, what is happening? So this is the geometry, basically. This is a fundamental domain for this picture. And topologically, you've got a torus cross interval here, open torus cross interval, if you go all the way up to infinity. And then you're gluing these two disks together. And so you take torus cross interval, and then gluing the two disks together puts on this handle body, or this one handle, I mean. Okay. All right, and again, we can deform this. So we can choose A, B, and C. We've got 6 degrees of freedom. They're all complex numbers. And several years ago, I actually wrote a program to do this so that I could see what the structures look like. So for example, I'm going to show you some of the output of that where we look at just 1 degree of freedom. So I'm gonna leave A and B fixed, and I'm gonna vary C in this path. Let me show you what happens. So let me bring down these slides. Okay, so here's our path of structures, and we start out with the structure that we've seen before. I should say we're looking at the universal cover here. So there's this translation by A and B in vertical and horizontal directions. And this is what you get when you start out with T is equal to 2. And we're going to decrease T. So you can see that these circles that are identified, they're getting smashed together a little bit until they bump. And then the fundamental domain has to change to keep this a manifold. So you get a new circle popping out. And you can keep going, and more pop out, and more and more and more. And then they'll start bumping across these translations, and circles pop out of those, and so on. But you do get these fundamental domains appearing at each step. And then eventually the program will crash, because what happens is you're getting infinitely many circles. in the limit, and computers aren't very good at handling infinitely many things. Okay, so that's as far as I was able to take my program. All right, so let me go back to my original slides. Again, the limiting structures were pretty interesting and complicated. And so again, it would be interesting to know what's going on there at the boundary. All right. Okay, now we're going to go to the topology. So we need to, we want to be able to relate topology to geometry. And this is a topological definition, but it's going to, we'll see, maybe not until my next talk, part 2, that this is exactly the sort of topology that you need in order to get geometry out of the structure. So what do you start with? You start with a 3-manifold. It has to be compact, oriented, irreducible. This means there are no essential 2 spheres. Atoroidal, there are no essential tori. We're going to take a non-empty boundary. Otherwise, we would be talking about closed manifold. That's a different talk. And we're never going to take a 3-ball. And we're never going to take a solid torus. Okay. On top of this, you take a special collection of subsurfaces sitting inside the boundary. And these have to include all of the incompressible tori that are on the boundary, and also a collection of incompressible annuli. And we say that this pair, MP, is paired if every pi1 injective map of a torus is homotopic into P, and every pi1 injective map of an annulus is homotopic into P. All right, so again, we need some examples. So let me, right. So, okay, so just let me say one more thing. So these are going to be the hyperbolic ones, and P here stands for pinched or parabolic. These are going to correspond to the elements that end up being cusped, and that's why they're tori and they are annuli. And everything that should be a cusp must be contained in one of these P's. So these tori and annuli that satisfy these properties. Okay, so I put the definition in smaller font up in the corner here so that you can compare when we look at these examples. But going back to our 2 examples we've been talking about, we have the surface cross the interval. And if you take the empty set for the pairing locus, then this is going to work. It's orientable, it's irreducible, there are no essential tori embedded in the middle. All the other elements vacuously hold. Okay. For the compression body, this C, our T2 cross the 1 handle, you have to throw in the inner boundary here, this T2 cross 0 into the parabolic locus, otherwise it will break number 1. But if you throw it in, then you get a paired manifold. And you can add to this. You don't have to just stick with your the required parabolic locus. You can throw in other curves as well on the outer boundary. This is supposed to be on this outer boundary. Here, if you take an annulus corresponding to a little neighborhood of a longitude, then this is also going to be a paired manifold. Okay, so some non-examples. If instead of taking an annulus, you take a meridian, so this bounds an essential disk, this is not going to work. And the reason why is your annulus has to be incompressible, but this is a compressible annulus with a compression disk right there. And the hyperbolic geometry is not going to like that. You're trying to tell the geometry that you need to pinch this trivial curve, whereas it really should be homotoped away rather than turned into a parabolic element. Similarly, if you take your surface cross the interval and then you pick for your annulus, you pick 2 parallel annuli, one on either side, then this is not going to work because this is going to break number 2. Here's a map of an annulus into this the manifold where you've got one boundary component on this side, one boundary component on that side, and that is not going to be able to be homotoped into P. Okay, so these are the situations that will block hyperbolic geometry. All right, so let me tell you about some of these major theorems in infinite volume 3 manifolds. The first one was proved in 2004 approximately by Ian Agel and independently by Caligari and Gabai. And the tameness theorem says that if you have a hyperbolic manifold with finitely generated fundamental group, then it must be homeomorphic to the interior of a compact 3 manifold. So this, as a corollary, you get a standard compact core, which is associated to N. So if you have any hyperbolic manifold with finitely generated fundamental group, you know there must be a compact manifold such that N is the interior of this. And the boundary here will it'll contain a subsurface that has all the cusps inside of it. So if you take N minus a union of all these cusps neighborhoods, then you get this topological manifold that's homeomorphic to your paired manifold M comma P. Okay. There are different types of structures, hyperbolic structures. Geometrically finite structures are simpler ones. And geometrically finite structures have finite-sided fundamental domains. And you can see for these a way of telling whether you are geometrically finite or not from these sorts of pictures is that you will see the conformal boundary. So what do I mean by that? I mean, there's a bit, you have this finite-sided fundamental domain. This is the, in the case of the compression body, here's the fundamental domain would look something like this, where this comes out at infinity. And when I say the conformal boundary, what I mean is you've got this bit of C, this Riemann sphere, C union infinity. And it's going to be cut out. There are going to be pieces of it that you're not going to see. So for example, everything under these green disks is not part of or you don't see it from the manifold. But all of this black stuff here is part of a conformal boundary. And remember from our metric on hyperbolic space, if you've got 2 points, so let me just draw it over here. If you've got 2 points, say on these lines, and they're moving down, because the metric rescales Euclidean by height, the height here is going to 0. So these points are getting infinitely far away. If you're going to put some area there and push it down, that's going to give you something infinite volume. Very, very quickly, that's going to blow up. All right, but it's a geometrically finite structure because they're a finite-sided fundamental domain. So this one here is a little bit more complicated of a geometrically finite structure. I can try and draw a fundamental domain, probably looks something like this, I think. But again, you've got this region here that's showing this conformal boundary. So we're going to call these ends, these regions with conformal boundaries, we're going to call these geometrically finite. And then similarly, any quasi-Fuchsian space is also geometrically finite. I haven't drawn for you a finite-sided fundamental domain, and I'm not going to dwell on this, but you can take the convex hull of this limit set here, and that will give you something finite-sided in 3D in the case that it's quasi-Fuchsian. All right, so if you keep pushing these structures out to infinity, though, you get something that does not have a finite-sided fundamental domain that's completely legal. And these are called geometrically infinite structures. And we call the ends geometrically infinite ends. This picture here, this came from my computer program. And again, I can't really show you a geometrically infinite structure because the computer just does not do well with showing you infinitely many faces. But you could see from the example that you're just getting clusters of these planes reaching in and covering up all the black. And that's what's going to happen when you approach this geometrically infinite. This is the limit over here, or beginning to be the limit, again, of these quasi-Fuchsian structures. You start to get a space filling curve. And again, this is from Thurston's paper from 1982. So associated with the geometrically infinite structure is what is called an ending lamination. Roughly, there's going to be a sequence of closed geodesics that exits the end. You can think of these as the loxodromics that are gluing these faces in this compression case. Each of them corresponds to some geodesics. They're getting smaller and smaller and smaller. They're getting closer and closer out to the boundary, and they're not going to be contained in any compact subset. And these geodesics have a limit, and they limit to a lamination. And this is called the ending lamination. And the second major breakthrough of the 2000s was the proof of the ending lamination conjecture. This is proved in one case by Minsky, 99, and then Brock-Canary-Minsky proved it for incompressible boundary, and Bowditch has a different proof that works in the compressible boundary case. But basically what it says is that you've got 2 manifolds with the same standard compact cores, So homeomorphism between compact cores. And moreover, if their ends, if the geometrically finite ends happen to have the same conformal boundary, in other words, there's a biholomorphic map between conformal boundaries, and if the geometrically infinite ends have the same ending lamination, then these must be the same hyperbolic three manifolds. So in other words, we don't have Moss-style rigidity. We can deform the hyperbolic structure. But if you fix once and for all the topology and the ends, the end invariants, conformal structures and lamination, then this uniquely determines the hyperbolic structure. And then the third major breakthrough was the density theorem, and this followed quickly once we knew the ending lamination was true. This was proved by Oshika and by Namazi Soto. Both of them credit lots of other people, but they kind of put the cherry on the top. And if n is a hyperbolic manifold with its associated paired manifold MP, then there is going to be a sequence of geometrically finite hyperbolic structures that converge to n. So n can be really ugly, it can be geometrically infinite, it can be or geometrically finite, but you know that there's a sequence of geometrically finite structures converging. And the convergence is a little bit different in the two papers. The original conjecture was talking about the algebraic topology, which we haven't really mentioned. This is a topology of the convergence of the fundamental groups. Namazi Soto, in their proof, they actually get this to work in both algebraic and geometric topologies by fixing the paired locus. And so we are going to work with this particular version because the topology we've been talking about in the previous talks is the topology of geometric convergence. We want these manifolds to converge in the geometry. All right, so this brings us to the landscape in the 2020s. Given a hyperbolic three manifold, finitely generated fundamental group, no matter how ugly the three manifold is, we know that it is the interior of a compact three manifold, so it's tame. We know it's uniquely determined by its end invariance, the ending lamination theorem, and we know that you can approximate it by geometrically finite manifolds, by the density theorem. So this means that you have all sorts of these tools in 2020 that you never had before. And I am going to end my first talk there and pause a minute for questions.
I have maybe either too elementary or too complicated a question way back at the beginning. So when you had initially embedded S cross I into H3, yeah, what was that?
Here we go. Found it.
Yeah. And so then you said you did slight deformations. So what are the rules for those deformations? Is the S still required to be embedded with its original hyperbolic structure or not necessarily?
No, not necessarily, no. The requirements on the deformation, I mean, you need to deform so that it remains a discrete group, so that you have a copy, so the gamma still is the fundamental group of a surface, basically, is but that's it. And yeah, so you're not going to keep the same nice geometric, totally geodesic surface in the middle. You lose that. But you get some pleated structures is what they're called. You get these bent structures on either side if you take the convex hull. That's the best that you can do at that point. Yeah. Yeah. Other questions? Yeah, step back through my slides slowly. Okay, if there aren't questions, let me carry on. So second talk is a little bit, I think I'll keep a little bit shorter. It's about topology versus geometry. So when does the topology guarantee that there's a hyperbolic structure? The first theorem along these lines that I'm mentioning, it's not first in chronological order, but hyperbolization part 1 is due to Thurston. And he showed that if you have a paired manifold, so this is a topological condition, then there must exist a geometrically finite hyperbolic three manifold such that the standard compact core is this pair. And we saw that with ours. So we had our our Fuchsian surface is an example of this. And our structure on the compression body is another example of this. Okay, I guess even more, I didn't mention this, but when we have this, remember we could pick curve P also. So this was another one. If we add this annulus to our parabolic locus, what this means is this topological curve on the boundary should be shrunk to a parabolic. And topologically on the boundary, that's a curve that runs between these two disks. And the way to get a pinch structure there is you just rotate these disks until they have a fixed point when you do this gluing together. So they end up a fixed point like that when you try and glue them together, and that'll give you this particular parabolic. Okay, so once you've picked your parabolics and you've picked your manifold, then you can obtain a hyperbolic structure. All right, so the benefits of this theorem, there's some structure with some end invariance, but an obvious question is, if I have my topology and I have any end invariance, so I choose the end invariance, not you, can I still find a hyperbolic structure? And in the case that everything is geometrically finite, then this is classical, and it goes back to work of Alfors and Bears that was done in the 60s and 70s. And it's written in the language of the 60s and 70s, so it's kind of hard to read the proof, but there's some treatments of this. Dick Canary, for example, has a nice survey paper on this that's more recent. But basically what this one says is that the Teichmuller space of the boundary completely controls all of the space of geometrically finite structures. So precisely, if you have an incompressible boundary, then the Teichmuller space is equal to the space of geometrically finite structures in the incompressible case. In the compressible case, it's a covering of that. So there's a covering map from Teichmuller space geometrically finite structures, and you have to quotient out by orientation preserving homeomorphisms of M. Okay, but in any case, a point on the Teichmuller space will give you a geometrically finite structure. And then even beyond that, so what happens on the boundary of these spaces of structures? This is a realization theorem. It was proved by Canary in one direction in '93. He showed that it's necessary, and Namazi Soto in 2012 showed that it's sufficient. But so if you give me a paired three manifold and a collection of end invariants, then you can turn this into a hyperbolic structure, except in two very special cases. So you have to be careful. If M is this surface crossing interval, so this one of these running examples we've been looking at, then recall we were not able to have essential annuli in there that run from one boundary to the other. What this statement number one says is you can't have the limits of those except essential annuli either. So your ending laminations have to have transverse intersections. Basically what this means is, so i.e. Not the limit of essential annuli. So you remember you had these geodesics exiting the ends, the geodesics are approaching this lamination, and if the geodesics are paired up so that you have these annuli, then that's going to be problematic. Number two deals with the compressible boundary case. So in the case that you have a compressible boundary, so such as this compression body, then the other condition is that you cannot have limits of meridians. So no limit of meridian. Okay, so again, these two problematic cases, they show up here now in ending laminations in the limiting behavior. But otherwise, everything will work. Okay, so then the question that I needed an answer to for a particular application was, what happens if you change the manifold? So does it become hyperbolic? Does it stay hyperbolic if it is hyperbolic? Yesterday we looked at Dane fillings. We saw that if you do this one on n Dane filling on a crossing circle, then you can put in two n crossings of a knot, for example. So it'd be nice to be able to say in the infinite volume case that if you do something like this, that you stay hyperbolic. just a quick reminder of what topological Dane filling is. When you have a three manifold with torus boundary and you have a slope on that torus, well, I should say this should be one torus boundary component. You could have other boundary components off here doing other things. But you take a slope on this torus, and then you attach a solid torus to it so that it bounds a disk. And Dane filling has been an important tool in three manifold topology since the 1960s, when Wallace and Licorice showed that every closed orientable three manifold comes from Dane filling. In the finite volume case, you have a result of Agel and Lackenby proved independently in the year 2000, and this is called the sixth theorem. What they showed, if you've got a compact manifold with torus boundary components, whose interior admits a complete hyperbolic metric. So if this is for all torus boundary components only, so this is going to be finite volume. And you have a collection of slopes on distinct boundary components, then remember, so if this is hyperbolic, means that these boundary components are going to be tori, they're going to look like tori on horospheres. And your slopes are just going to be some sort of, you can put them in the Euclidean metric there. So they're going to have a geometric length. And for the sixth theorem, you require that this is strictly greater than 6. Okay, so on a collection of disjoint embedded horospherical tori, you have this. Then you can guarantee that the Dane-filled manifold is hyperbolic. And the way that they prove this is they used Thurston's hyperbolization theorem. They showed that this length 6 implied that there are no spheres, disks, tori, or annuli. And Dave and Saul and I needed this in the case of infinite volume manifolds. So when we say a tame hyperbolic three manifold, we just mean finitely generated fundamental group. It's going to have some sort of a paired manifold associated with it. And again, we can take some of the boundary components will be tori, and we're going to take slopes on those with length strictly larger than 6. Then you can get when you do the Dane filling, this M with parentheses, this means the topological Dane filling. When you do the Dane filling on this, you get a paired manifold whose interior admits a hyperbolic structure, and the end invariants are identical to the ones that you started with. So we're changing the paired manifold entirely, but we can get the same end invariants. Okay. And for the proof, it actually ends up being really similar to the proof in the finite volume case. So we need to show that we need to show the definition of a paired manifold. So we need to show this is a paired manifold, and then we just need to show these other two conditions for the realization theorem. So it needs to be irreducible, meaning that there are no essential spheres. It needs to be atoroidal, no essential tori. It can't be a solid torus. It's sufficient to show there are no essential disks for that. Here we can reduce this case into showing that there are no essential annuli, or embedded annuli, and then here we have tori again. The three-ball, it can't be in a three-ball because the original unfilled manifold is irreducible, so you don't even have to worry about this. But again, so we're looking for spheres, disks, tori, and annuli. And for the realization theorem, we need to show that in this special case of a product manifold, your ending lamination isn't a limit of annuli, so we get annuli again. And in this case here, for the compressible disk, you need to show that your ending lamination is not a limit of disks. So really, we're just looking at these same surfaces. And then quickly, the way that the proof goes is if you have this problematic surface sitting inside your topological Dane filling, then this surface, so let's pretend it looks something like this. This is your problematic surface, problem surface. It's going to be intersecting these Dane filling solid tori. It has to intersect them because it doesn't exist in the unfilled thing. The unfilled thing is hyperbolic, okay? So you'll get a collection of meridians on your solid tori that you've added. And when you drill these out, so drill out these solid tori, then you're going to get a punctured surface. And in fact, you're going to get an essential punctured surface, and the punctured surface can be pleated. So there is this an essential, sorry, they should have the word punctured in it. So what does it mean it can be pleated? It means you triangulate it topologically, and then you straighten that to be a geodesic triangulation. And it's not going to be something straight, but it's going to give you this bending. And it will inherit things like an area. And then this is a theorem of Borowski from the 1960s or 70s. I can't remember. But anyway, he showed that this area of this hyperbolic surface is at least pi-thirds times all of the area that's inside the cusp. And in our case, that's going to translate into pi-thirds times the length of the cusp boundary, which is the length of a meridian. Okay, so if S meets the cusp, if it meets these Dane filling solid tori m times, then the area is at least 2 pi times m. On the other hand, because we have this pleating, we have the Gauss-Bonnet theorem. The area is negative 2 pi times the Euler characteristic. If it's a sphere, that's 2 pi m minus 2. If it's a disk, that's 2 pi m minus 1. If it's a torus or annulus, that's 2 pi m. And from the previous slide, the area is also strictly greater than 2 pi m. And in all of these cases, you have a contradiction. And that is the end of the proof. And I was going to say something very briefly about these other realizations, but they're quite similar. You use limits of annuli and you use limits of disks. So I will stop there. Yeah, so conclusion, we have a paired manifold, the realization theorem applies, and so therefore we have the sixth theorem. Okay, that is the end of this second talk. All right, so let me pause again for a second and see if there are any questions so far. I'm gonna have some water while I pause. Okay. Last chance, any questions? I'll let you ask questions at the end on parts 1 and 2, even though you had another chance earlier. Okay, so let's go to finite volume methods in infinite volume examples. And this is a joint project with Dave Futer and Saul Schleimer. And this is we're gonna start all over. This is a completely new talk, part 3. What Dave and Saul and I were interested in was an effective geometry change under Dane filling result. So remember from Dane filling, you plug in a solid torus. You can do something like you can put twists into a twist region of a knot. And for the application we had in mind, this is a long time ago, we had nice explicit geometry before we did the filling. And then we wanted nice explicit geometry after we did the filling. And if I'm remembering it, actually, we may also have had applications that go the other way. We may have had a nice explicit geometry after the Dane filling, and then we wanted to drill out a cusp, and we wanted nice effective geometry over there as well. So yesterday we talked about this geometric Dane filling of Thurston, and I'm going to go back through that a little bit, just briefly. If we have M with the torus boundary component and the interior has a complete hyperbolic structure, then the torus boundary is going to be, it's not part of the interior of the manifold. So it lies off to infinity. So it's going to lift to a point at infinity. And what we've been doing is we often, in our pictures, we've been lifting it to the point at infinity, one copy of it, but there will be other copies. And these, if you look at like SnapP, for example, you'll see horoballs around each one of them. But a tubular neighborhood of the boundary now is, this lifts to a ball, a horoball, and you're going to see a fundamental domain for the neighborhood is going to look like a parallelogram here on a horoball, like so. So in the complete structure, so this is somewhat, we get some messier diagrams for this last bit of the talk, but in the complete structure, our horoball is, we can think of it as all the points that are above some fixed height, and the horosphere is the set of points on that height. And this horosphere will give you a a Euclidean structure, basically, on a torus. Okay, so if you have, in fact, it's complete if and only if you have a Euclidean structure on this horospherical torus. And now remember, yesterday we bumped this a little bit. So if you deform the complete structure very slightly, then you get something that is incomplete. And on the torus, you get something that looks like this affine structure. So instead of putting parallelograms together, you have something like these more generic quads. And as you start gluing them, you will spiral around and you will miss a single point on the horosphere. And then as you take the product of this up to infinity, you're going to be missing the whole geodesic. So if you take the completion of this, then two things can happen. Number one, you may be crushing the boundary completely. So you may get a 1-point compactification, and this is not going to be a manifold. So this isn't very interesting from a topological point of view, although the geometry is still very interesting. The other thing that you might do is you might get lucky and you may be just attaching a closed geodesic to the boundary. And when you do this, while attaching a neighborhood of a geodesic, we know what that is. That's a solid torus. And so this is going to give you something that is homeomorphic to Dane filling, but you have this geometry now attached to it. So Thurston's hyperbolic Dane surgery theorem says that if you've got this situation, so M is a 3-manifold with torus boundary, and the interior has a complete hyperbolic structure, then you can deform in a neighborhood of infinity, basically. So for all but finitely many slopes, M of S admits a complete hyperbolic structure. And this has been a really great theorem, and it's had lots of amazing applications since it was released in theorems in Thurston's notes in the late 1970s, early 1980s. But it doesn't work for our particular purposes because it's not effective. So we don't know what the non-hyperbolic slopes are. So to make this more effective, there's a school of thought that used cone manifolds. So this is Craig Hodgson, Steve Kirchhoff, and others, but they were really the ones who started this. Rather than deforming the complete metric just however you want, you fix on deformations for which you attach these geodesics, but when you take the completion, you get a cone manifold. And what that means, so I've tried to draw this schematically. So this is supposed to be a tube around a geodesic. And if you take a disk cross-section of that tube, like so, then if it's a complete hyperbolic metric, at the core of this tube, you're going to have angle 2 pi. If it's not, you could also have angle between 0 and 2 pi. And in this case, you're going to get a cone. And this geodesic in the middle, this is going to be the singular locus. So it still is a topological Dane filling, but hyperbolically you get the singular locus, so it's a cone. There's a singular set. But finally, if you keep going, if you deform to angle 0, then you end up with a cusp, and this is complete again. So you get a complete cusp structure when the angle is 0, and you get a complete filled structure when the angle is 2 pi. So the idea of this Hodgson-Kirchhoff program is if we start with a cusp, that's angle 0, let's deform all the way down and show that you can get your deformations all the way to angle 2 pi. So this is the result of that program. They have a couple of papers from 2005, 2008, building upon previous work that they'd done through the 90s as well. So this was a lot of hard work, but a very impressive theorem. So if you have a 3-manifold with torus boundary, the interior has a complete hyperbolic metric. And if you have a slope whose normalized length is at least 7.515, then you can guarantee that the Dane filling is hyperbolic. And moreover, you can guarantee that there is a deformation through cone manifolds. So the angle goes from 0 in the cusp case to 2 pi in the complete case. Here, the normalized length is just the length on a horosphere divided by the area of a horosphere. So this is actually, if you can do a calculation, this is independent of how high you put that horosphere. Okay, and another nice thing about this particular proof is it's a lot of analysis. And so you can actually get bounds on the geometry of these cone manifolds as you go. So remember, Dave and Saul and I, we want effective bounds. This is a good start. They show that this happens. If you look carefully at their proof, the idea is maybe you could say more. And other people had done this. So using cone deformation, techniques, you can obtain bounds on the change of geometry. So either if you deform from, this is a cone angle 0 in the cusp case, or cone angle 2 pi in the filled case. And the results that you get will depend on the normalized length in the cusp case or the length, the usual length in the filled case. And so Brock and Bromberg in 2004, they came out with a filling theorem that used this, that told you about geometry change. So in particular, you fix your favorite j greater than 1 and epsilon greater than 0. And then once you do that, there exists a length so that if you have a hyperbolic manifold with a closed geodesic of length at most L, then the identity map is going to restrict to a J by Lipschitz diffeomorphism outside of a neighborhood, an epsilon neighborhood of this geodesic. So the drilling theorem tells you can drill, and their method is cone deformations. You can drill this geodesic and you'll get a J by Lipschitz diffeomorphism where you get to pick the J. So this is exactly the sort of thing we're looking for. We get this, I get to pick the J, I get to pick the epsilon, and then I get this cone deformation. The problem is right here. There exists an L, but they do not tell us what it is. So again, unfortunately, this is an ineffective theorem. So we actually needed something a little bit more strong. And with a lot of work, we came up with it. So this is our effective drilling theorem. It appeared on the archive in 2019. It's been accepted, but hasn't appeared in print. So if M is a finite volume hyperbolic 3 manifold and you have a geodesic in there, a geodesic link, and the length satisfies effective theorem. All right, I am not going to read that to you. You can see it's a bit of a mess, but the point is this depends explicitly on epsilon and on J. So I can tell can get my computer, I can tell my computer what J is, what epsilon is, and it can find all the slopes that I need, or sorry, all of the lengths that I need to worry about in this case. In this case, you have by Lipschitz inclusions from thick part of one to thick part of another, and vice versa. So here, by the thick part, this epsilon thick part, I mean all the points that have an embedded ball around them of radius epsilon over 2. So this will throw away all cusps, for example. And we also have a version of this. This is for a version for drilling. There's also a version for filling where we just run everything backwards. Okay, so this is really great. It's effective. Finally, we've had various applications that we were interested in, but it only applies to finite volume 3 manifolds, and it was a lot of work. So we want to apply it to infinite volume 3 manifolds, but unfortunately, we don't really want to redo all of that work. So the big exciting breakthrough for us was we realized that you can use the tools that I've outlined in parts 1 and 2 of this talk to actually get the result in the infinite volume case almost for free, where almost for free means only 30 pages, not 70. Okay, so here's our result. This is on the archive 2021. And now you get this effective result for tame manifolds. So if M is a tame manifold, sigma is a link, and you have a hyperbolic structure. I've actually, let's see, I've shown you the filling version, not the drilling. So if you have normalized length that's sufficiently large, so again, you can ignore everything in the black box, but this is effective. Then you get a hyperbolic structure, same end invariance, and by Lipschitz inclusions. So this is nicer than the 6th theorem because you know that you get this by Lipschitz result and a similar result in the filling case. Okay, I think I have 2 slides on the proof, one in words, one in a diagram. I'll walk through the words and then I'll walk through them again with the diagram. But it really is just, the idea is we're going to take this infinite volume case and we are going to turn it into an approximation by finite volume manifolds. And then we can apply our finite volume theorem over in the finite volume case, and the convergence will push it all the way through. Okay, so here we go. So we've got this link, sigma 1 through sigma k, and we're starting with a hyperbolic structure on this on the interior of this paired manifold. All right. So the 6th theorem tells us that we get a hyperbolic structure with the same end invariance on Dane filled manifold. So we're going to call this one Y. So we have part of the theorem already. We have that it's hyperbolic. We don't have any bounds at this point. So in order to get the bounds, we're going to apply some big theorems. So first, we're going to apply density theorem, which tells us that there's a sequence of geometrically finite structures converging to Z and sequence of geometrically finite structures converging to Y. And now I'm going to use, again, a theorem of Brooks from yesterday. Well, let me just state it. I should probably have reviewed it, but let me just state it. Brooks says that when you have a geometrically finite structure, then you can approximate it by geometrically finite manifolds that admit circle packings on their boundary. So we're going to take these ZNs and we're going to take for each one of them. I mean, I suppose I should do another subsequence here, but we're going to diagonalize in the end. So you get these manifolds that are circle packed boundaries, Wn converging to Zn, and circle packed boundaries Vn converging to Yn. And recall with the circle packings, so a circle packing is a collection of pairwise disjoint circles whose interstitial regions are triangles. They correspond on the boundary of infinity to hyperbolic planes. And if you dig out the half spaces around those, you're going to get something with these interstitial regions. Dig those out as well. So after you scoop these hemispheres out, you get what we call a scooped manifold. And we call these Wn and Vn. And these have geodesic boundary. If you double along all of these hemispheres, then you get something with finite volume and torus boundary components. Okay. All right, so here's the picture of what's happening. You start here with Z hyperbolic. You do a Dane filling and you get here Y with the same end invariance. This is by the sixth theorem that Y exists. Okay, you use the density theorem here in the red to approximate these by geometrically finite manifolds. You use Brooks' theorem here in the black to approximate these by circle packed manifold or scooped manifolds. And then you double and you have an isometric inclusion into the doubles of these. And then over on this side, we have these finite volume manifolds with a torus boundary. And so we get our results over here. We have this bi-Lipschitz result in the thick part, but now go backwards. So for n large enough, you're close enough to Y that this bi-Lipschitz result is going to hold all the way back to here. And so by going around the diagram, you get the bi-Lipschitz condition. And that's the end of the proof. Okay, and that is also almost the end of my talk, but let me just conclude with this one slide. This was really fun for me. So I really like this idea of transferring a result in the finite volume case to the infinite volume case. And so now I feel like we've got this really great hammer, where this hammer, this is a really great hammer, right? We're little people here, and this is a huge hammer that came from all of these major theorems in infinite volume hyperbolic 3 manifolds. But we have it, it's there, we should use it. And so I will stop here. That's the end of my talk. Thank you.
Okay, let's all thank Jessica for her third talk. So does anybody have, well, I guess we're doing questions as part of the discussion session. So let's transition to that in a moment. But before we do that, let's take a moment to also thank Jessica for her entire series of talks. Okay, so let's move into questions and discussion. If anybody has any questions or anything they'd like to discuss.
So can anything be said when you take a quotient of hyperbolic space by a non-discrete group of isometries?
Yeah, can anything be said? Well, that's actually a really good question. So if you take a quotient by a non-discrete, I'm scrolling back to this slide here. These incomplete structures are non-discrete quotients. So sometimes you can say something interesting, yes. Typically you end up with a mess. So for example, if these pictures that I had here, right, if you're, you move through these spaces of structures, and if you accidentally bump something that's non-discrete, then the computer just goes crazy and crashes because it tries to draw, it's drawing infinitely many circles that get bigger and bigger and kind of fill the space. So it screws up with the computer, but mathematically non-discrete structures correspond to these incomplete sorts of things, and they can give you some information if you can control them.
So if the volume is finite, the group will always be discrete, right?
Sorry, what's that?
If the volume of the quotient is finite, the group will always be discrete, right?
If it has finite volume, if it's a finite volume complete hyperbolic structure, then yes, it's going to be a discrete group. Yeah. Yeah, and I guess I didn't really say here, discrete. Discrete just means that there's no element converging to the identity, right? So no non-trivial sequence. AN inside of your gamma converges to the identity, and you need that to get a real non-singular manifold out when you take the quotient. Yeah. Yeah, what else you can do? I mean, you can kind of, it probably, people have asked it, whatever, right? So you want to do something to these infinite volume manifolds, you do something to your group. It's probably been encountered somewhere, either on someone's computer program or they thought about it mathematically.
Are there other questions or discussion points? Everybody's worn out from 3 days.
I think so. This is where we all go to dinner, right?
Yeah. So
Carry on the discussion there.
So it's always good for folks who have enjoyed the talks to know a good resource, for learning more about them. Of course, I'm sure a great one is your book, which I've pulled up again. Are there other places that you would recommend that people look at, literature or exposition, or what's a good starting point?
So for the infinite volume manifolds, probably, let me, maybe I'll go back to the beginning. Can I even do that? It's too far away. I recommend the paper, Namazi and Soto is a pretty good read. This is on the density theorem. I don't remember exactly what the title was, but it's something about on the density of three manifolds. It's a bit of a long paper, but it's long because they do a really good job of the exposition. So it's sometimes hard to read these three manifold, the classical papers in the infinite volume literature, they're kind of hard to read because people had to dance around these three major structural conjectures. And so they prove something with certain cases. I remember having this discussion. I wrote a paper with Juan Soto many years ago, soon after these things had been proved. And he put in references to various things in the literature, and I went and looked them up, and it didn't say anything like what he said it said. And then I went back to Juan and said, what are you talking about? You've got all these extra hypotheses. He said, oh, no, we don't need those anymore because the tameness theorem was proved, or something along these lines. So Namazi Soto, when they wrote their density theorem paper, this is kind of the culmination. So tameness was known at that point, ending lamination was known. And they set up these paired manifolds carefully, and they go through some of these results carefully with a lot of good references. So I think this is currently my favorite reference to this sort of literature. There's also a survey paper by Dick Canary that similarly is quite well written after these major theorems were proved. I don't have the title of that one off the top of my head, though, unfortunately. I think that actually Namazi Soto may cite it. So, so start there for the infinite volumes is what I would recommend.
Great, thank you. Any other questions?
Can I ask a question, Jessica?
Yeah, sure.
You, at the end of your talk today, you said that you can extend the tool, use a tool in finite volume to the infinite volume. So I think this is a big question. Can you tell me what's the difficulty in extending the finite volume method, maybe tools for the finite volume method to the infinite volume case?
Yeah, so why couldn't you do it 20 years ago, I guess maybe is the question, right? So these tools now, we have these major theorems, I'm almost there, right? So here we have the density theorem, we have the ending lamination theorem, we have the tameness theorem, and these all came after the year 2000. And so all these results that people were proving in the finite volume case, why couldn't you just extend them before you had these tools, right? So now we can use these tools, we can approximate them, we can circle back them, we can double, we can get finite volume things. Before then, yeah, I mean, I guess it really, maybe I'd answer that question by just going back to this very first slide. Infinite volume manifolds are hard because they're not rigid. So there you have all these deformations that you don't have in the finite volume case. You have algebraic versus geometric topologies versus strong is where you can do both. You have strange things happening on the boundary that you didn't necessarily expect. And the literature is written in the literature of complex analysis. So if you're quite adept in that, then that's not an issue for you. But it's hard to read from some of this work from the 1960s.
Okay,
yeah.
Thank you.
Yeah, you're welcome. Not quite sure that I answered your question, but that's
yeah, thank you.
why it's a
Thank
lot
you
of
so
work.
much.